Hi guys, I'm Dhruva Juloori from Uber's developer platform. My work primarily focuses on handling continuous integration at scale. Today I'm here to share some of the insights about how do we handle continuous integration at Uber and a bit of my learnings too. Before diving into the topic, I would like to give some context about monorepos. A monorepo is a single and shared source of repository that hosts all or most of the company's assets. Instead of splitting the projects into multiple code bases or repository, everything is hosted at a single place. The benefits of monorepos are studied widely in software engineering community. Some of the key benefits include code consistency and standardization, simplified dependency management, and it also improves code shareability and reusability. Some of the leading tech companies use monorepo approach to host their code bases. So let's start with a problem. Why is green mainline a hard? Like, why is maintaining a green mainline hard? So the figure what you see on the screen is basically the state of the mainline with a commit points. And Alice and Bob are two developers. Basically, create a new branch from a certain reference point to introduce their changes. So Alice introduces the change C1 and Bob introduces change C2. Now both of them test their changes and all of the build steps pass. But when Alice tries to merge the code, all of the build steps pass on the main line. Pretty good. Bob tries to merge us and the build steps fail. Now, why this has happened? Because Alice and Bob tested their changes individually but not collectively. Now, so just imagine what could happen at scale when multiple or hundreds of people are concurrently committing to a single code base. So at Uber scale, we have about 4,500 plus engineers working from 10 plus global development centers, concurrently committing to six of our monorepos primarily, Go being the busiest, and then Android and iOS, and then followed by Java, Python, and web. Our monorepos handle a scale about 65,000 plus commits per month and are home to 1,000 plus microservices. And they facilitate about 100,000 plus deployments per month and host about 130 plus million lines of code, or even more than that as we are speaking. So, what are the drawbacks of Red Mainline? First one, delayed rollouts. So if the main line is broken, we would not be certain of or sure of when to release enhancements or features to the customers, which could potentially have a direct impact on business in terms of cost. The second one, hampered productivity. Developers will not be sure when to deploy or land their changes because they're not sure of the reason of why their changes are failing in the CI. And the next one, complex rollbacks. So when hundreds of people are concurrently committing to a single code base, it gets very difficult to restore back to the last known stable version because developers might have already created new branches and started developing. So no business wants to be in this state. So how do we solve this? Let's meet Submit queue. It's essentially Uber's merge queue. This provides an illusion of single queue to developers to submit their changes, and it guarantees reasonable SLOs for developers to land their changes quickly. It utilizes CI resources efficiently, and of course, always maintains green mainline at scale, even with thousands of changes per day. So, how does it work? So, in a nutshell, SubmitQueue broadly consists of four core components. The first one being enumerator. This component basically takes a queue of pending changes and constructs a binary decision tree of all possible builds for those changes, which we internally call it as a speculation tree. And then the profiler. This component takes the generated speculation tree as an input and lands the changes according to the landing order based on the predicted build times. Next, the prioritizer. This component tries to compute the probability of build needed for each node within the speculation tree using the landing order information and also by predicting the change success. And then the selector. This component basically schedules the high probability nodes in the CI as builds based on the resource availability. Now let's see how all of this works. So by walking through an example, so let's say there are three changes: C1, C2, and C3 arrived in the order mentioned. Now for C1, we only need one build. So, and we represent this build as B1, which is nothing but build steps for the main lines head H and the chain C1. For C2, the total possible builds are 2 because it has arrived after C1. So C2 essentially needs to be tested with C1 and also without C1. So here, the build B2 represents the build steps for uh, the head H of the main line and the chain C2, and B12 represents the build steps for C2 against the head H of the main line and chain C1. Now for C3, the total possible builds are 4. So in this way, if we try to construct the speculation tree for n changes, the total possible builds would be 2 power n minus 1, and this is not at all viable at scale. So we need smarter ways to schedule these nodes as builds in sci. So how do we do this? The first approach is conflict analysis. So basically, we assumed all the changes conflict with each other and constructed the speculation tree. So it means that this changes cannot be committed in parallel. So what if the changes can be proved to be independent? If the changes are independent, changes can be committed in parallel, and it also helps down to reduce the speculation space, which in turns reduce the number of possible bits. So how do we do conflict analysis? We leverage build systems such as Buck, Bazel, or etc. for any build system for that matter. So the intuition behind conflict analysis is two changes are said to be independent if they affect a disjoint set of build targets. For example, there are let's consider two changes, C1 and C2. Now, when we try to compute the build target graph of C1 and C2 when applied on the main lines head H and try to see like what are the build targets that are being affected, if there are any overlapping set of build targets among these both changes, it means that these both changes are conflicting with each other, otherwise they are not. So let's take a few examples. So in this case, the three changes C1, C2, and C3. C2 and C3 are independent, meaning that they're not conflicting with each other, but they both are conflicting with C1. So the total possible builds here would be 5. We reduced it by a factor of 2 since C2 and C3 are independent. Now, in this example, C1 and C2 are independent, but they both are conflicting with C3. So C3 has to wait until the decisions for C1 and C2 are made. That is either to commit or reject. So the total possible builds here are 6. Previously, there were 7, so we reduced by 1. So just imagine, like at scale, like when there are massive changes, the like conflict analysis can help us to like trim down the number of possible builds. But what actually if there are conflicts? Like that is pretty much possible, right? Like we cannot predict the nature of the requests that are incoming. So there are likely cases when a lot of changes are conflicting with each other. So we need more smarter mechanism to determine what to build. So here comes the concept of probabilistic speculation, where we try to compute the probability of build needed for each node within the speculation tree. So let's take an example. So as mentioned before, we need the build B1 outcome to make a decision for the chain C1. So since there's only one possible build for chain C1, we need the build B1. So the probability of build B1 needed is 1. But we would only need build B12 to make a decision for chain C2 either to commit or land if the build B1 is successful. The build B1 success essentially depends on the chain C1, nothing but the characteristics of the chain C1. So the probability of build B12 being needed is nothing but the probability of the success of the chain C1 within the submit queue. Consequently, the probability of build B2 needed is nothing but the probability of the failure of the chain C1. Now, For build B123, the probability of build B123 needed is nothing but the two changes being successful. That is, if the build b1 and if the build b12 is successful, then only you would need the build b123 to make a decision for chain c3 either to commit or reject. So in this way we could try to compute the probability of each node as nothing but a conditional probability. But there are few challenges. So let's take this case as an example. This is a tree for two changes, C1 and C2. But let's say C1 being a large change which affects a large number of build targets within the monorepo, and C2 could be a very trivial change, very small change. So in this case, all the possible builds of C2 have been finished in the CI and have the same outcome, but still C2 can only be landed after the build B1 is finished, because the chain C1 is pretty large, so the build time is going to be more than the builds of the chain C2. Now, let's take another case as an example. In this case, chain C1 and C2 are larger than the chain C3. So, all the possible builds of chain C3 with the both changes that are conflicting, C1 and C2, have passed in the CI and have the same outcome. But still, C3 needs to be weighted for the builds of C1 and C2 to be finished. So, we don't want this to happen at scale, right? So, if at all, if the changes are waiting, the possible conflict rate would go up, and the number of possible bills would also go up. So if we know that it is safe to land the change, we should essentially be in a position to land the changes as fast as possible once we determine uh, changes are pretty safe to land. So here comes the concept of bypassing large diff. So what we could derive from this concept is, changes can be landed faster if all speculative builds with conflicting changes ahead are evaluated and yield the same outcome. So this is nothing but a principle of commutativity. So uh, let's say there are two states. The first state being the mainline head hedge, and then C2 landed first, and then C1. The second state being the mainline head hedge, and we in this case we land C1 first and then C2. So these both states are pretty much the same, are equal. So the state of the main line when C2 is landed first and then C1 will be equal to the state of the main line when C1 is landed first and then C2. This is nothing but a commutative property. A plus B equal to B plus A, or A into B equal to B into A. So deriving, basically taking the principles of commutativity into account, we introduce the concept of bypassing large diff. So our goals on how to determine like what to build is, basically we have two goals. So we want to prioritize the builds in such a way that we schedule all the speculative builds for the possible bypassing changes, and we only schedule the most likely builds of the changes which cannot land faster than the conflicting changes ahead. So now taking these two goals into consideration and putting into a mathematical notation, we derive the following formula. So basically, the probability of build needed for chain C depends on the build outcomes of the conflicting changes ahead and the ability of the respective change to bypass its conflicting changes ahead. So now the next question is, how do we determine the build outcome and the ability of bypassing? So by predicting the change success and build times. So how do we do it? We leverage machine learning. So we train classification and regression models to predict change success and build time, and our prediction accuracy is about 97% for our classification model, and mean absolute percentage error for regression model is about 5 to 7%. So the key features of our machine learning models are um, change characteristics and some of our dynamic speculation features, and we also use like some of the developer attributes. So the key or the most impacted features are the number of affected targets and number of git commits in a single diff, and number of files changed, number of added lines, etc., and the status of pre-submit checks. And also some of the speculation features, such as the position of the node in the speculation tree, the height of the tree, etc. So now summarizing the whole thing, so this is pretty much the architecture of submit queue. So basically four core components. The enumerator takes the pending changes and builds a binary decision tree of all possible builds by doing conflict analysis. And then the profiler takes the generated tree as an input from the enumerator and lands the changes according to the landing order by predicting the build times. And then the prioritizer tries to compute the probability of build needed using the information of the landing order given by the profiler and also by predicting the change success. Then the selector takes the top probability nodes, or probably top ranked nodes, and schedules these nodes as builds in the CI. And once the build outcomes are completed, it makes a decision either to commit or reject a change based on the outcome. So submit queue has been at Uber for from quite a while. So we started from 2018. From then we've been trying to innovate and evolve. So we've been adding new features and feathers to the system each year. So our last major introduction of features are bypassing large diff and build time prediction. So once we roll out these features, we saw a significant impact on resource usage in CI. So the dashboard what you see here is determines the resource usage of monorepos, basically number of builds per change. So we have like a 21 week rollout, and we can see the pre and post week rollout stats. So we were able to achieve like a mean reduction of 53% reduce in number of possible builds for our major monorepos, Go, iOS, and Android. And in terms of CPU consumption in CI, we saw a reduction about mean reduction about 45% for our monorepos, Go, iOS, and Android. And our P95 waiting times improved by 37%. It means that we are able to land changes 37% faster than what it was before. And these are some of the resources that we published before. So our first paper being keeping master green at scale was published at Erosis 2019. And then bypassing large diffs in submit queue is an Uber engineering blog. And CI at scale, lean, green, and fast is a paper that we published recently at ICSC 2025. That's about it. So, if anyone is interested to know more or talk about continuous integration at scale or chat more about Submit Queue, I would be more than happy to answer any of your questions. Thank you very much.